wat hier is gaan nou hierdie praatjie kyk.
Laat jy worry nie.
Okay. Ja, ek het nou topologie lesing, so ek kan gewoonlik nie soos hierdie praatjies bywoon nie, want so ek organiseer hulle, maar ek het in hierdie tydskrif het ek my meesterswiskunde module.
Okay.
So, maar ek doen eintlik my meesters hier in fisika, maar ek is
oranje.
ja.
Dis pragtig. Okay. Okay, so good afternoon, officially then. I'm Dr Nienkemper-Swanepoel. I'm from the Department of Statistics, and quite recently we have formulated a research group, as you can see there, a Center for Multidimensional Visualization at Stellenbosch, and in short we call ourselves MOVISU. And yeah, that's a very exciting opportunity for us to really focus on multivariate visualization and also collaborate in a more formal setting. But today I'm going to share not a lot of detail, but show ideas of things that interest me. And over my years, I have come across a lot of missing data problems, and then of course visualization, as you can take note of the MOVISU angle there. So the topic there is more philosophical, I would say, data lost but not forgotten. So the whole science of missing data, why am I so interested in it? So when data is not there or unobserved, I definitely don't forget about it. So I try to tackle that. So this is just the MOVISU team. And you'll also see this collaborator's name pop up in some of the slides as well. So we are the founding members of MOVISU. So Damien did give me just a bit of background that it's supposed to not be a technical talk and just, as I said, sharing ideas, but I wanted to tell you where my journey with mathematics started. So of course in high school, well, school, but especially in high school. So I'm from the Free State. I attended school at Oranje Meisie School for 12 years in Bloemfontein, and I really had an amazing math teacher, which just made all the difference to me. So when I had to decide what to study, I decided something in mathematics. And I came across statistics, so I did all my degrees up until masters at the University of the Free State in mathematical statistics. And then in my master's year, I started this investigation into missing data. And then I moved to Cape Town and I did my PhD at Stellenbosch. And here I got into multivariate visualizations, but the amalgamation still with missing data. So just out of curiosity, are you familiar with the concept of missing data? I mean, you know the word. Okay. So breaking it down, what does it mean? It means something that's incomplete, unobserved, lost, gone. Okay. So it's data that we don't have anymore. Maybe it never existed, but maybe it's gone for a reason. So just to kind of tell you about the types of missingness, I have this very small survey example where we have 3 variables. So those are the columns, and we have 3 samples. Now in my field, we call the rows of the data matrix the samples, or the observations there. So we have measurements on all of these variables, as you can see. So the types of non-response, so that's another way of calling a missing data point missing. We say unit non-response if an entire row is missing. You can't do anything about that. The entire set is gone. Item non-response would be that some of the observations are missing. You can definitely do something about that. Incomplete responses would mean they're not correctly captured. So if this was a field where someone had to type in the province as opposed to selecting from a list, and they just said Western, then, okay, we know it's Western Cape in South Africa, but it's incomplete, so that would be an incomplete response. So that's just a type of missingness. That's not the cause of missingness. Okay, so in statistics, we believe that data goes missing due to a random process. This process we call the MDM, the missing data mechanism. And there are 3 formal definitions of these mechanisms. So I'll just read them with you. So missing at random, that's when a missing observation depends on something that is observed in the survey. Okay, so what that means is when there's a dependency between a missing and an observed observation, means there's information that we can utilize to try and fix the problem. Missing completely at random is when your missing observations are completely independent of observed or unobserved. So it's completely random, as it says, completely at random. that this missing data point occurs. Missing not at random, that's a complicated one, because then your missing values depend on something that's unobserved. Okay, so those are the three classifications. Typically, we always work on the ignorable non-responses. Those are the first two bullets, missing at random, missing completely at random. But a lot of research now focuses on the missing not at random mechanisms, which are quite difficult to model. But the techniques that I'll show you, ideas, will be based on missing at random and missing completely at random. So this is a very basic way of just seeing where the missing values occur. We call these missing maps or missingness maps. So this can just show you, really, it's just color coding your data matrix, where it's missing, where it's observed. So it tells you, for instance, the first one, it's a univariate missing pattern because it only occurs in one variable, one column. Monotone would be that we see it's an increasing amount of missing. As you can see, completely observed, and then we move increasingly to more missing observations. An arbitrary pattern, that would be, again, falling in the missing completely at random category. So why I'm showing you this is just, these are ways, not modern ways, of trying to understand what type of missingness am I dealing with. First, what was the type of missingness, then what was the cause of missingness, and the patterns can tell you, or give you an idea, can't really tell you. So I won't give you detail on approaches, just an idea. So the easiest way, of course, would be to ignore this whole missingness problem and move on. But of course, that would be a big mistake, because you are, in the first place, losing sample size. You're decreasing your sample, and you're going to create bias, because you're going to unrepresent the population you're trying to sample. So classic techniques which are not advised would be to delete. Deletion methods, there are various ways. Easiest way is just to delete the rows of any non-response, and then you only use your observed information. So reduce sample and, of course, bias. Then a slightly better way to handle this we call single or simple imputation methods. And this is where you replace each missing value with a plausible new value. Now, the most classic way would be to take the mean of a column and replace those values with the mean. But again, you are unrepresenting, or you are underestimating the variation that could occur, because you're just replacing everything with the mean. So it solves your problem, but then you have one complete data set which could be used further, but it will create bias. So in literature, we say the superior approach, or a lot of people say, is to use multiple imputation, MI. And as the word tells us, we're going to have multiple plausible values per missing entry, and then we have multiple completed data sets. So what you do then is you perform whatever analysis you're interested in on each of these completed sets and then combine them. So that is the idea of multiple imputation, and that is the approach I follow as well. Within the field of multiple imputation, there are various applications, various algorithms. I'm not going to tell you about those. Something that I didn't add here explicitly is Rubin's rules, but Rubin, the name Rubin, he has a set of rules which we use after we've implemented multiple imputation to combine the estimates. So just thinking you have a data set, missing data, and then you impute it 3 times, so you have 3 completed sets. Then you perform whatever analysis you want on these 3 completed sets, and then you combine the results. So the thing of multiple imputation is, the aim is not to have a complete data set. The aim is to have a final inferential statement, so a final conclusion that is not underestimating your variation, which is a realistic reflection. So imputation, again, I don't want a complete set. I'm not going to compare the complete and the original sets one by one. I want the results to be as close to what it would have been if I had the complete set. That's the philosophy of multiple imputation. So that's the one leg. Very brief introduction of what missing data is, and then BIPLOTS. Who has heard of BIPLOTS? Worked with BIPLOTs? Okay, so you know plots, visualizations. So BIPLOTs are generalized scatter plots. But let's start with the first bullet. I tell you that it's a multivariate visualization, which means if you have more than two variables that you want to display simultaneously. So thinking of a scatter plot, you have your y and your x-axis, and you represent two variables, a bivariate relationship. So bi in BIPLOT refers to two modes, two entities. It actually does not refer to the dimension of the visualization. So it enables you to represent the rows and the columns of the matrix simultaneously. And as I said in that first case, the rows are the samples in my terminology, and the columns are the variables. Okay, so the scatter plot idea is extended to more variables. So we know we have two axes in a two variable case, x and y, but now we can increase the number of axes to be equal to the number of variables. So if you're thinking of a large data set, of course, this can become very cluttered, overplotted, but there are ways to get around that. But the idea is that your axes represent the number of variables. You'll still have the number of plotted points, which are the observations, which represent our rows in the matrix. And I'll show you BIPLOTs now, but just those last 2 points there, says the positioning of the axes refer to how the variables are correlated, right? And the proximity of all the points, all the coordinates in the visualization tells us something about the association. So thinking always of a survey association, we want to know how closely related would sample 1 and 3 be. We can see that they're on the same age group, but they're from different provinces. That's just a very simplified example that we have. So based on provinces, sample 2 and 3 are highly associated, right, that we can see. Based on ages, sample 1 and 3 are highly associated. So that's the type of thing that we would want to see in how close the points are situated in the map, in the BIPLOT display. So here on the left, we see what a scatter plot is. So just the x-axis, y-axis, and we can look at the relationship. Here we see a negative relationship, negative correlation between the variables. And what we can do is we draw a perpendicular line to those axes and read off the value on the calibrated axis. Okay, that's how we read the scatter plot. So that is definitely just extended to the generalized case. So if we work with a multivariate problem, of course, we have a higher dimensional problem. So we would have to use some dimension reduction. In the techniques I'll show you, we use singular value decomposition. So the idea is that we want to express this multi-dimensional problem typically in 2 dimensions, because we can read it and print it on a paper, and so, but we can do 3 dimensions, of course. But then, as you see in this one, I'll show you more, but you have 10 variables. So we have 10 axes actually in this map. And then we have all of these observations. So what you could do then is draw perpendicular lines to each axis for a sample point, read it off if it was calibrated. And that's how you would be able to read it off. And of course, this is all based on geometry to be able to interpret these angles between the axes, because they're no longer orthogonal axes. So the actual angle between them will tell us something about the correlation of those variables. Okay, so the very basic idea then, starting with the scatter plot, we have 2 variables, 3 observations, and we can see that we can read them off as is. If we go to the first observation, on the x-axis we have 100, y-axis we have 90. Let's look at the third one there, so 90 on the x-axis, 110 on the y. Okay, we all know this. Now I can just move the axes. Nothing has changed. If I go back, okay, this is more the standard way of seeing it, but then you can move the axes without changing anything. I can still read the values off. 2 has a value of 70 on the x-axis, 90 on the y-axis. Okay, so nothing has changed. This is just showing the perpendicular lines, how we read it off. Then I can also tilt it, so I can rotate it slightly. Nothing changes, we can still interpret it. So this can be my new display. Now the axes are no longer 90 degrees in the traditional sense. It's slightly tilted, but still variable 1 and variable 2 are expressed in the dimensions that we saw. Then we can add a third variable. Okay, without using a biplot, we can definitely have this three-dimensional display. Slightly trickier to read off, but you can just keep track of where the axes are. So variable 1 here at the bottom, variable 2, variable 3, our vertical axis there. And you can read off the values as you see there. But now I don't want to use that three-dimensional display. I want to use a biplot, which I can look at in 2 dimensions. So this is now adding the third variable. So we no longer have orthogonal axes. We have an axis for each variable. So you see variable 1, 2, and 3. And as I quickly said, the interpretation method is the same. We project perpendicularly to an axis and we read off the calibrated value. So for variable, let's go back, variable 2 here, I should have, this is the red dot, 110. Then for variable 1, I should have 90, which it is there. And for variable 3, I should have 130. So a 3-variable problem can be exactly represented in 2 dimensions. So it would be a perfect representation as you see there. So for all of these variable measurements, for the 3 observations, we will be able to read off the value. So that's how the biplot works for a continuous case. We can also add a 4th variable. Now, where's that 4th variable? Obviously, the display changes with each addition. So we have variable 1 and 2, 3 and 4. Now, if the variables are, or the axes are perpendicular, it means they're not correlated. If they are close, so the angle between them is small, they are highly correlated. It could be that they are negatively or positively correlated. We see with variable 1 and 2, the small values start at the top, larger values at the bottom, so they are positively correlated, right? Both of them increase to the, let's say, the lower end of the display. Okay, so just showing you then with the 4th sample point that I've added there. Again, all those lines are just to show where the values are pointing towards. So now that I have increased the dimension of the problem, expressing it in 2 dimensions, you see in this bottom table is the actual values that I read off from the calibrated axes. So you can see it's not perfect, but you want to, there are various approaches, of course, so it depends on how you reduce the dimension, but ultimately you want the best 2-dimensional representation of your original data set. Okay, so some of them are quite well represented. If we look at observation 1, you see how close just 0.3 deviation, 0.1 deviation, again 0.1, 0.1. So very good representation in 2 dimensions. Okay, so we can look at things like what's the predictivity of the biplot, what is the fit of the biplot. So you can look at some performance measurements to know how well you can actually display this in 2 dimensions. Okay, so that's a biplot, and I'm sure you will now know how to tell someone about it. It's very useful. There are so many variations. The most classic way is the principal component analysis biplot for continuous data. And my research focus over the last couple of years was on categorical data. So I wanted to first show you how to interpret a biplot and then move to my type of biplot. So for categorical observations, as I'm sure you're aware, so the numerical cases or the continuous cases measure on a numerical scale. Categorical, we measure on a qualitative scale, so fixed categories. The ones that I'll be showing you today are nominal scale variables, so they're unordered categories. And the biplots for a categorical case, the specific nominal case, you'll have 2 types of coordinates. So you won't have axes, as I just showed you for the variables. The variables will also be represented by a set of coordinate points. And to distinguish, we call the sample coordinates, which represent your rows, just the sample coordinates. And then the variables we call the category level points. So the points representing each response category level. I'll show you an example just to put that together. And again, in biplots, we use distances, or as I said, proximities. So the closer coordinates are positioned in the display, that shows a high association between the response profile. So we can definitely utilize that. Okay, so a small example here where we have individuals, I think 7, sorry, and we have these 5 variables, measurements taken on them. It's not really important to fixate on what happens, but for categorical data sets, we break it down in a binary way. So we call it the indicator matrix. So each variable is represented by the number of columns, which relates to the levels of that variable. So gender has the 2 levels in this example. Hair has 4 levels, fair, gray, brown, dark. Region has 3 levels. Work has a couple of levels. Education. So all the variables have their own response levels, and these are represented in a column, and then a dummy variable 0, 1 tells us if it belongs to that response level or not. So this indicator matrix is a core step in this construction of the BIPLOT. The category level points I refer to, each will refer to one of these columns in the indicator matrix. So this is how the BIPLOT could look. In the header there I tell you it's a multiple correspondence analysis BIPLOT, MCA, which is specifically aimed at nominal scale data here. And prior steps to this, we do singular value decomposition to reduce the dimension, and then I display it here in 2 dimensions. So as I did with the continuous case, I want you to be able to interpret the BIPLOT. So you would see that these gray squares, they are the samples. So the individual names, and then these upward pointing triangles, those are the category level points. So for hair, the yellow ones here, we have the 4 yellow triangles because they are the 4 levels of hair. If we go back, 1, 2, 3, those 4 levels there. The same with all the other variables. So we want to look at the positioning of each. So we'd see individual George is at the cross product there of your category level points of the other variables. Mostly it would seem that it's always centered, and then around that individual you would see its corresponding category levels. So if we look at George, male, brown, England, manual, school, so you can see brown hair, that's the closest to George. Male, school, manual, and England, those are in closest proximity to George. But I want to say that with a bit of a disclaimer, when I say closest proximity, sometimes in the 2-dimensional representation, they won't seem the closest if you take a ruler and you start measuring that. Of course, this is an approximated display of a high-dimensional problem. So it might seem, just looking at it, sometimes they don't seem in closest proximity, but the idea is that the category level points around that individual. So let's just look at a couple more. And these are just convex holes that you just draw them around the points, the extreme points of the levels that I'm interested in. So these are showing us that this guy is surrounded by the category level points of interest. We see Jane there on her category levels. Same for Eva and Harriet, and then Jeremy. So looking at it, just quickly going through it, we can see that these samples are surrounded by their category level point. So if you would have selected one of them, the idea would be that in closest proximity, you would be able to identify the response profile of that individual by using the BIPLOT. So what it means also, Harriet and George, they are closely situated here in close proximity, so they have similar profiles. Okay, there will be differences, of course, but you can see that there are overlap between them, and that is how we can utilize the strength of associations. Now, maybe you can already see why this is important. So say now some of the variables have missing values for Harriet. So Harriet is closely associated to George, so I can use a type of an imputation that uses the strength of the relationships to impute. And as I said, I would always use multiple imputations, so I would have multiple plausible imputations to fill up the data sets using associations of other samples. So that's the idea behind the approaches. So to show you an amalgamation then of what we've done, we call our method GPA bin. Now the name bin actually comes from Rubin, that I told you about the combining rules of Rubin. And GPA refers to what we call generalized orthogonal procrustes analysis. I'll show you what it is. But so GPA bin is a BIPLOT technique to combine visualizations after multiple imputation. So it combines BIPLOT theory and multiple imputation. So just to show you a simulated example, what's important is that we just see, okay, well, I have 1,000 rows in my data matrix and 5 columns. These are categorical data sets that I simulate initially from a continuous distribution, and then I categorize it. So that's not very important. What is important is I create missingness. So I delete 10% of the observations according to missing at random. So that means I have created a dependency when I delete it. Okay, so that I know there's supposed to be associations between observed and missing. And then I choose to do 10 multiple imputations with an algorithm referred to as MIMCA. MIMCA stands for multiple imputation, and the MCA stands for multiple correspondence analysis, which I've showed you in the BIPLOT. So combining those techniques. So the idea is, the background that I gave you is, I created a data set, I deleted 10% of the observations, then I created 10 updated data sets, which are now complete. Again, 1,000 rows, 5 columns, using that MIMCA algorithm. Then I construct 10 BIPLOTs of the completed sets, and that's what you see. You have 10 completed data set visualizations. Without labels, it would be too cluttered. But what you can just see from afar is you see similarities in broad patterns. Right, you can see it looks like kind of a frame. These three at the top seem very similar, and then this is just a reflection about the y-axis. Again, some reflection there. So they look similar, which is good because I have imputed 10 times, which means I don't want 10 replicates, but I don't want them to be completely different, because then my imputation process is also not working. It should be, the variation should be incorporated, but it shouldn't be completely varied, complete noise. Okay, so great, I have 10 visualizations, but this is not a solution. This is also a problem, because how do I write 10 reports? How do I conclude? So what I show you here on the left is I superimpose all of those triangles that you saw. Those are the category level points. It is just noisy. So in statistics, we say it's noisy, a lot of variation, can't use this. So what I do is I take a centroid configuration, that's what I call it. It's basically just the mean of each of the 10 representations pooled together. So these are the black squares you see there. They are the centroid points. So this is just the idea of GPA, generalized procrustes analysis. So you want to match a target, or rather we call it a test T, to a target. Okay, so you have two configurations and you want to match the one to the other. And you can do this by means of reflection, rotation, translation, and did I say rotation, reflection, translation? I'm missing one. I can't remember the other one. Let's see if it gets to me as I go through the steps. Okay, so we center them always. We want them to have the same center. Okay, so if we are matching B to A, so A is our target. If you look at the points there, I hope you can see it. So it says A2, A1, A4, A3. So the idea would be to match B1 to A1, B2 to A2, and so on. So we can see here that, okay, they are both centered now, but I need to rotate this, and I need to reflect it, right? Scaling is the other one. I didn't say translate, scale, rotate, reflect. So systematically, I apply these changes without forfeiting I preserve the distances. Okay, so the ratios there are preserved. So this sketch shows us then that we are, in a sense, flipping, so rotating B, so that B1 can be aligned with A1, and then we also stretch it then, and we also rotate in order to get them to match. And that is where procrustes comes in. So apparently in Greek mythology, Please don't, I know there's a recording, but now I don't even have the year or anything. But it was this, he was like a guest house owner in that days. I don't know the exact word in that times. But he would want their guests to fit properly on the bed that he had. And he would stretch them or cut their limbs in order for them to fit on this bed. And he was Procrustes. Okay, so that's the idea that you can see we're stretching B to fit onto A. So that's Procrustes analysis. But because in my case I have 10, this is for 2 images, 2 configurations, we have to generalize it. So what you see here we call orthogonal Procrustes analysis, so 2 figures, but generalized GPA for what I do. So this just shows you that the centroid configuration is now used as the target, and then I match the 10 displays to that target. So there are some gray shapes there showing you reflections that happen and scaling. I can't show everything, but those 4 steps are applied then on each of them until we reach an optimal display. Okay, so this is done iteratively. So now I have 10 displays that look more similar, but still not a solution, but it's much better. So this is what we had before GPA, and now this is what I have after. Okay, so I have variation, which I want, but it's now aligned, optimally aligned. So to show you what this gives us in the end, you'll see to the left is a complete data set and then completed, meaning imputed. And to the left is what the display would have been, my initial display that I have all complete data points. And on the right is the 10% deleted values after this whole mission that I just told you about. They look similar again. Broadly speaking, I see positioning are similar, but I see variation. The way that I see it is with these open circles, they are more, they're not on top of each other, because actually in the left you have 1,000 circles, you just don't see them because they're all on top of each other. But on the right we have variation, which is very important if you work with imputation. As I said, you don't want to be unrealistic, you need to represent the variation. So this is what I call my GPA bin BIPLOT. This is something you can interpret. Okay, so this has been through a lot of testing, through simulation of various distributions, and it is a well-fitting representation of the original proximities. Now, with that I mean, if you would have interpreted this BIPLOT with your BIPLOT principles, the interpretation of the GPA bin BIPLOT, it actually preserves those interpretations. So it's a good visual representation of missing data. So we have started the extensions to continuous data and also compositional data, where we use various types of BIPLOTs. So it's still very much a growing topic for us. So that's just the one thing. And then a shorter part of the presentation, I want to tell you about how we use BIPLOTs to identify the missingness mechanism. Okay, so the first part was to show you how to visualize multiple imputed data sets. Now I want to show you how to use visualization to try and understand the cause of missingness. So why it's an important problem to tackle. You can't just apply any missing data technique on a data set because it's unobserved. You need to know why is it unobserved, what type of missingness, the whole introduction I gave you. Because otherwise you would just be applying copy and pasting techniques, but it's not applicable. So you need to have a clear understanding of what this could be, or what the cause could be. And as I said, missingness, we know that there are dependencies that we can utilize. Okay, so to identify a particular missingness mechanism, we might be able to relate that to a dependency between missing and observed. And then the big important aspect is, BIPLOTs, as I said, we use the distances in the display to interpret the strength of associations. So we can definitely use the proximity approach, link that to the association between samples. And that's the idea. How we can do that, just a small example. If you have a categorical data set on your left, those NAs are the missing values. The indicator matrix I told you about with the category levels per column. All of these variables have 3 levels, so 1, 2, 3. You can see some of them in the columns. So we have 3 columns per variable, and then zeros will be inserted in these blocks where they're missing. You can't do anything with that. So we use an approach called single active, which means we create a new column with a query there, just showing us it's a missing column. And then we also do the dummy classification, 0, 1. What this does, it allows me to look at subsets of the data set. So now I can separate missing and observed, and I can also apply a type of multiple correspondence analysis for this specific data set. Now that allows me to visualize missing and observed separately. So I'm just going to show you the visualizations of missing and to kind of motivate why this idea could work. So you'll see that these category level points, the one in words, they all have NA, so they're missing. And we can clearly see there's a grouping, right? 3 of them are placed in the left corner, 1 at the top. So what we can say is cluster analysis. We cluster groups together. We see a clear separation there between the top and the left bottom points. Now, I want to know, does this separation imply that there's an association, right? Because that will help me to get to the mechanism. Why is it missing? And in the chart, you'll see I have also simulated this example, inserted a lot of missingness, half of it, deleted half of the values according to a dependency structure, so according to missing at random. And what I try to show is by introducing a dependency, I can see separation, clear separation. Now these values you see here, it's a silhouette coefficient. It's a coefficient that we measure, and if it's close to 1, it shows good separation. It's close to -1, poor separation. But what we are actually interested in is to see if it's above 0.5, that is an indication of clear separation. Below 0.5, poor separation. If I try to force 3 groups, of course this is not splitting well. So that is how the idea came about. So we said, okay, let's simulate all of these cases, see if we can separate them into clusters. If the separation coefficient is above a threshold, this is maybe an indication of a dependency. Below a threshold, it's independent. To show you quickly how this works, in this last column, and I'm going to show you, I don't even know how many now, 9 slides after each other. And I want you to just look for patterns. You'll see the top row is 10% deleted, 30 and 50% deletion. It's not important what these distributions are, the first 3 columns, but those are missing at random mechanisms, which means I'm looking for a pattern. Okay, to the far right, I'm looking for independence. So let me scroll, and then you see, so look left to right. So we see patterns, then we see this blob. In the right column, it's just blob, and then we call it a swarm of points. They're just surrounding that middle center. Patterns, blobs, pattern, kind of a blob, patterns. You see, it keeps happening. Right, even more so. What made me very excited, of course, in a preliminary sense is I can see a difference. The first 3 columns show something that looks like a pattern. The last column keeps showing me this centered point, the green circles on the center surrounded by a random spread of the others. And that is exactly what I want to see. I want to be able to separate points or coordinates in the left displays, and I don't want to be able to do it in the right, because then I have found my cause of missingness. So we found that that actually works, right? That was the idea. We, of course, have some guidelines, but I want to show you an application, just a shiny application that we wrote for this, which you can play with. Let's open, I don't test it now before. Let's see, maybe it works. Yeah, okay, so it's a bit small now, but what you can do is you can set your number of variables, your number of samples, so rows and columns of the matrix. you can select between two simulation distributions, and you can choose the cause of missingness beforehand, because you want to check now, how does it look differently or not. So missing at random again, that's when they are dependent, completely at random, independent. And then you can force the number of clusters, but what we found is the most suitable amount is to select a third of the number of triangles that you have, the category level points. A third of that will give you the optimal number of clusters, but you can force it as well. So then it will also tell you here what the silhouette coefficient is, and then you can, from there on, decide, did it actually work? So I didn't check one before, but let's see if I change my distribution. I want to make a bit more dramatic. Okay, so what I've done is I've 400 samples, make it 700 samples. And we have 6 variables. These category levels, you can change. Those are just the number of columns in the indicator matrix per variable. They will be varied. 30% missingness according to missing completely at random. So what you see is the complete subset. We don't interpret it at this stage, but that's your complete biplot. Missing subset, you want to know if there is separation. And if you see that circular shape in the middle, that's similar to the green ones on the right that I kept showing you here. So that looks similar to that, just a swarm of points there, which shows us, well, this could be missing completely at random because there's no particular pattern here, which is then also shown in that silhouette coefficient there, 0.3, it's quite small for you now, which means it suggests it's missing completely at random, which is what we've simulated. Okay, let's hope if I change it to more, okay, it's better. So it's close to 0.5, okay, that's obviously lower than that. But we can see a difference in how those samples are placed. See, I've seen a couple of them, of course, now, so it's easier for me to see. But also the category levels are not surrounding that center plotted points. So that's the idea behind it. Then we also look at specific examples, and you can actually also upload your own data and test, but it should be a categorical data set, so it should be in this format more or less. It can be numbers, but it will be used as a category level, not as a numerical value. Yes, so we can look at this Titanic data set, which is also a simulated set. And what was nice when I did the application, it's in an R package, this data set. I completed the analysis and said, okay, based on what we've learned now, okay, this is missing completely at random because of the coefficient and the way that it looks. And then I also read in the paper that they've actually simulated it according to completely at random, which I didn't know at that stage. So that was a good confirmation. It was a very fun moment for me, of course. But yes, so that is just the application that we have to also explain the methodology. So what I told you today was just to give you some terminology really on missing data, what it entails, very important, what causes missingness, how can we define it, how to interpret a biplot, how to, for continuous and categorical, and then the idea of using biplots for multiple imputation, and then how to use biplots to identify missingness. And that's all I wanted to share with you. Do you maybe have any questions? These are just R packages. Do you use R statistical software? Okay, so these are some of the packages. I see I should have a space there. Yes.
Does the entire rotating and fitting the different ones on top of each other, does that work in multiple dimensions as well? So if you have a biplot that's in 3D, for example.
Yes, good question. So how can you have the dimension of the biplot, so the coordinates of the configuration, that can be, if you can't see it, that's fine. I mean, if you can't see it in 2 dimensions, you can have multiple dimensions, but the 2 configurations that you match, there are 2 ways, but best is if they are the same dimension. So the target and the test are the same dimensions, but if they're not, we use a technique called padding. You can pad extra columns for those dimensions, but yes, it's not limited to 2 dimensions. Yeah. But the aim here was to help someone which will interpret the biplot, and that's in 2 dimensions. But we did test on the full dimensional space to see for accuracy. There are some improvements, but it wasn't, I want to say, the success was not worth the computational efforts. Yeah, but it is possible. Yeah. And yes.
Thank you, Johan. How far can you go in terms of dimension? Can you apply the algorithm on the problem that is in hundreds or even thousands of dimensions? Because I'm worried with how you do the computation if you're increasing the size of P.
Yeah, so it relates to his question also. That was specifically for the GPA part, but then what do you do if you have a lot of dimensions, a high dimensional problem? Now, in terms of the computations, I mean, if you use an HPC, you won't be limited necessarily for that, but the singular value decomposition can be quite computationally intensive, the actual reduction step, the dimension reduction step. But there are authors that use a systematic or sequential SVD, singular value decomposition, which has improved the computational time. So there are approaches already being developed for higher dimensional reduction problems. Then with respect to the biplot, if you have 1,000 dimensions, to visualize it, if you think in terms of the axes, you would have 1,000 axes. So of course, you can't see that. There will be just ink on the page. But there are ways that we use density plots to see where there would be a higher density of those axes, or we have we use axis predictivity, so we only display the axes with the highest predictivity, so we don't display axes which would not have a good calibration. So there are, for the visualization aspect, some ways to get around it, but of course it would be very, I would say, tricky to visualize 1,000 dimensions appropriately in 2 dimensions, but it's not impossible. Yeah. No. Yes.
And just a fun observation I made is a 3D scatter plot is sort of like a biplot when you display it in 2D, because
yes.
you're sort of squishing the axes down.
Yeah, true. Yeah, just pointing out the 3D which relates to the biplot. Yeah, no, that's true. Yeah, but I'm also used to biplots, of course, but I find it much easier to read than that 3D dimensional one. But yeah.
Also, I guess in 3D it depends which angle you squish it down from.
Exactly.
And I guess for biplot you sort of find the best one.
Yeah. Yeah, that's true. Yeah. Yeah.
So this is sort of off topic.
Okay.
If I understood it, if you're doing the biplot thing, and eventually you try and maybe not make predictions, but read all information from the biplot.
Yeah.
Then the way you generate the biplot with the missing data, you're never trying to like figure out what the missing data is. You're just trying to figure out like what it could be so that your eventual conclusions are like as accurate as possible.
Exactly.
So are there other techniques under like the field of missing data where you actually try and figure
interpolate,
out what all these missing values?
Yeah. So there are, the first one I can just mention is nearest neighbor techniques, which relies on the distances again between observations and putting them in little neighborhoods, so again clusters. So there are nearest neighboring imputation methods, which does exactly what you're hinting towards, where you use the proximities and then try to, I want to say, match or find the most suitable placement based on the neighbors in that map. So that's one way. It relates to interpolation, so where you want to put a new point in the display and read it off, so try and estimate a new point. So yes, it remains interesting where I feel you need, if you do it that way, where do you get your variation if you want multiple plausible calibrations? But I think there's open field for more questions like that, definitely. But you're right, I went from imputation to visualization, not visualization to imputation, which is very interesting. Yeah. And I think just thinking out loud, you can then play with the dimensions. So maybe have multiple imputations based on various dimensions. Even though you can't see them, but you can get your variation there maybe. That's interesting. I'll write that down. Yeah. Anything else? Yeah.
Yeah, sorry, a bit of a shadow question. I don't have any knowledge of the subject whatsoever, but would the whole point of this be to help someone who isn't as versed in the statistics field to actually get an idea of the data?
Yes, so exploratory analysis is where BIPLOTS fit in. So visualizing something, a data matrix for someone to let them to grasp what's going on underneath the surface, really. So yes, it's very important for that user engagement, I want to say, understanding the data. So exploratory analysis is one of your first fronts of data analysis to kind of lead you to more questions. Yeah. Yeah. Good observation. Yeah. Okay, anything else? Yes.
If you have data and then you generate a BIPLOT for that data, is that stable, or like, are there multiple good BIPLOTs that look completely different from the same data?
Yes, so it depends on so many things because you can have various distance measures that you use. I mean, we typically use Euclidean distance, but it depends also on the situation, what you are looking at. So the distance measure will have an impact, the dimension reduction approach would have an impact, and then also similar displays, but, or rather they look different, but they have the same interpretation based on the distances. So there are measures that we can use to determine the best fit, the best representation, but there are, I want to say, a lot of variation in that construction step almost, yeah. Yeah. Okay, well, thank you so much for your time and attending. I hope that sparked some interest.
Yeah.
Yes.
So, are you, just some background, are you all undergraduate students or what? I don't know anything about the group. Yeah.
I am a master's student.
Yeah.